Welcome to Brain Vision.
Our question says to use figure 49 as reference, and it wants us to show that for points along the positive x-axis, the axis of the wire, the magnetic field B is 0. Okay, so we can go ahead and do that, and we'll indicate this as part A. So consider a small element on the rod, a small element of change. We'll call this element DL at a distance r from the point Q as shown in the figure. So from the Biot-Savart law, the magnetic field at point Q is going to be equal to, well, of course, it's B, the magnetic field, is going to be equal to mu naught over 4 pi times the integral of the current I times dl. L is that infinitesimal length change that we were talking about, cross vector r divided by r cubed. Okay, and again, r is the distance that we're considering from the point Q on the figure. And so since the point Q is along the length of the wire, then DL and R are parallel. So we can tell that DL is, we can say parallel, this is the symbol for parallel, with R. Since that's true, DL cross R is 0. Because the cross product of two things that are parallel is 0. Well, you plug 0 into that integral, and anything times 0 is 0, so therefore the magnetic field B is 0. And that is our proof. We can box that in as our solution for A. Part B says to determine a formula for the field at points along the y-axis, such as point P. Okay, so consider the small element d, dx on the rod. So we're going to let the distance between the element dl and the point P be little r. So from the right-hand rule, the magnetic field at point P, due to the current in the wire, is out of the page as shown. So we're going to call out of the page the positive k hat direction. So what do we have? We have B. We'll indicate this as part B. We have the magnetic field B. Sorry, the cursor got stuck there. Let's rewrite that. There we go. Is equal to, we'll pull everything out of the integral that's a constant here. So we have mu naught times I divided by 4 pi. And then the integral here is dx, that's what we're integrating with respect to, times sine theta over little r squared. And then this is all going in the out of the page direction, or the k hat direction. So we're going to use some trigonometric identities to simplify this a little bit. So from looking at the graph, we have r is equal to y over sine theta, because sine theta is equal to y over r, or opposite over hypotenuse. So r is equal to y over sine theta. Or in other words, you can rewrite this as y times the cosecant of theta, because 1 over sine theta is cosecant theta. And you also have, from your trigonometric identity, x equal to negative y over the tangent of theta. Because tangent is opposite over adjacent, so then x is equal to negative y over the tangent of theta. So this is equal to negative y times the cotangent of theta, because 1 over the tangent of theta is the cotangent of theta. Okay. Well, in our integration, we have dx. So if we take the derivative of x, then we can get dx. So differentiating x, we have dx is equal to y times the cosecant squared of theta d theta. Okay, that's because the derivative of the cotangent of theta is the cosecant squared of theta d theta. All right. So now we can plug this back into our expression for d of x. So we have an expression for r in terms of theta, and we have an expression for d of x in terms of theta. So we can put everything inside the integral in terms of theta. We ran out of room on this page, but let's go ahead and do it on another page. And we find that b here then is equal to, again, we have all the constants pulled out front. So we have mu naught times I divided by 4 pi. And then inside the integral, we have y times the cosecant squared of theta times the sine of theta. And this is all getting integrated with respect to d theta. And then this is divided by y times the cosecant of theta. And then this is all squared because we just replaced r with y cosecant theta. So that all gets squared. And then, of course, this is going in the k-hat direction. So we can very easily simplify this. We have things that are going to cancel. This cosecant here gets squared, right? So that cosecant cancels with this cosecant squared. And you have a y squared on bottom and a y on top. So that y cancels with the squared term. So you just end up with a y on the bottom. Y is a constant, so we can simplify this even more. This comes to be mu naught times I over 4 pi times y. And then now we're integrating with respect to sine theta d theta, which is a much easier integral. Of course, this is in the k-hat direction. So you integrate with respect to sine theta d theta, that just gives you cosine theta. So you have mu naught times I over 4 pi y cosine theta. And of course, this is in the k-hat direction. And at the extreme limit here, this is equal to mu naught times I divided by 4 pi y. And in the extreme limit, cosine theta becomes the distance d divided by the square root of d squared plus y squared. Still in the k-hat direction. So you can box that in here as our solution for part B in the